Okay, now we're at Kirchhoffs voltage law. This was developed by Gustav Robert Kirchhoff, and this is the second of two laws. His first law was Kirchhoff's current law, and I have a lesson out there on that as well if you want to go check that out. But Kirchhoff's voltage law stated that the algebraic sum of all voltages around a loop is equal to 0. So we need to look at that a little bit closer. He's talking about the algebraic sum. We'll have to understand what he means there, and he's also using a term called a loop. We need to figure out what he means by a loop. Let's look at a circuit here. This circuit has a battery in it. We should be used to this symbol. And we have 3 resistors. We should be used to those symbols as well. I have some nodes here labeled, and so this is a term of a point of reference that I'm calling a node, and I reference it with a letter, and I show with a round circle, a dot, that that is a node that we're going to be referencing. So I have 3 of those here. Another new symbol that I haven't used previous is this symbol right here, and that is the ground symbol. So this circuit will be grounded, and for that reason I have not labeled these 2 points right here with letters. Why? Because electrically this point right here, or ground, is the same point right here and the same point right here, and in essence it's also the same point as the negative terminal on the battery. And a good example of this would be your car. So in your car, the positive terminal runs through a wiring harness to all of the different devices, and the negative terminal is grounded to the chassis of the car. And depending on the device, some devices just get grounded to the chassis of the car to complete the circuit, and others have a wire pulled back. But in your car, your negative terminal of your battery is grounded, and very similar to the fashion that I have shown here. And there's just a note showing that I have added a ground. Now we have a new term that we're going to use, and it's called a voltage rise. And a voltage rise is an increase in voltage, simply stated, or a way of more accurately stating that is you're traveling from a more negative reference to a more positive reference. In this case, we're literally traveling from ground zero, the ground, up to whatever potential that battery is bringing us up to. And when we do that, we show the more negative side with a negative symbol and the more positive side with a positive symbol. And we're used to that as far as batteries go, but we're also going to use it in other portions of the circuit as well. Now this is a term you may be more familiar with, and it is voltage drop. A lot of people will use this more commonly in the field, or you might have just heard it at home. If your lights dim at home when the air conditioning comes on, that is a symptom of voltage drop. And someone might have used that term before. But here, a voltage drop is the opposite of a rise. It is a decrease in voltage, traveling from a more positive reference point to a more negative reference point. Okay, and we're still going to use our plus and minus symbols here. The reason we know this is a voltage drop is because we're traveling from a positive, more positive location to a more negative location. We have a voltage drop here across that resistor, and we have a voltage drop here as well. And we denote those also with a plus and minus side. We're moving from the more positive to the more negative as we are here. Now I can state these as the voltage drop from B to ground, because remember I said this whole line here is what we are electrically calling ground. So B to ground, that would be that voltage drop. C to ground would be that voltage drop. This voltage drop would be termed the voltage drop from A to B. So that's a good way to state those. Now here is a mathematical formula to say the exact same thing that this sentence here says is the algebraic sum of all the voltages. Well, I'm showing a subtraction sign here. What he's saying is if you take your rises and you add them to your drops, and your drops are going to be negative. So, whatever voltage this is, the voltage drops around here are going to be the opposite of that. They would be negative in polarity. And if you'd add those two together, you would get 0. I'm just terming this a drop. So, if this is 9 volts and we say that's 3 volts, I would say 9 minus 3. I'm not going to say this is a negative 3 volt drop. I think that can be confusing to people. So I like to state it this way. Either way is accurate, how he has it stated here or how I have it shown here, but I think this is a little bit easier to understand. So let's just look at this with some references on there. So I have denoted the battery as V0. The drop across AB here, the resistor at AB is V1, and the drop across B to ground as V2, and the drop from C to ground is V3. So now we're going to bring in another term. Remember, we had this term loop, and we didn't quite describe that yet. So he's talking about voltage rises and drops. And like I said, we had 1 rise here, and we have 3 drops. But he's saying that the algebraic sum of all voltages around a loop is equal to 0. So let's figure out what he means by a loop. A loop is a complete circuit from one end of a voltage source to the other end of the source. So I have a loop right here, right? I can show that. There's one of my loops. It goes from A to B to ground, which is in essence back to the source. Okay, so that is a loop, but it does not include this resistor here. It does not include C to ground. So I'm going to have more than one loop in this circuit. So here is a loop, and let's look at the other loop here. So the other loop is going to go from the positive of the source here, from A to B to C to ground. Okay. Now, one of the things I want you to notice is V1 is in both loops. Okay, so that voltage drop is included in either loop. And that makes a little sense because V1 is going to carry some of the current that is going to go in this direction and some of the current that is going to go in that direction. And we learn that with Kirchhoffs' current law because we have 1 in and 2 outs. So that's why it's important to know both Kirchhoffs' voltage law and Kirchhoffs' current law. So if I look at loop 1 here and I just apply his voltage law to that, I have my rises and I have my drops. Okay, so what are my rises? My rises are V0. Okay, so there's V0. And my drops are V1 and V2. See, I'm going from positive to negative. That's a drop. I'm going from positive to negative. That's a drop. And that is all of the drops that I have in L1. So I add those two together and I subtract them from V0, and that must equal 0. Okay, that's how to apply the law in that loop. Let's look at loop 2. Again, just restating what he has up here. And so we still only have one voltage rise here, only one source of voltage in this circuit. So V0 is going to be my only rise. But here I have V1 still, but I'm adding it to V3. Okay, so for this loop, I'm going through V3 and then coming back to the other end of the source. Okay, let's apply some numbers to this. Okay, so loop 1, we're going to have a 12 volt source for V0, and we're going to have a 3 volt drop here at V1. Okay? So we know from the previous slide that V0 minus the V1 plus V2 is going to equal 0. Let's actually do the math here. So if you say 12 volts, that's what we have here at the battery. That's my rise. It's the only voltage source I have in the whole circuit, so it can only be my only rise. And then I have my two drops. One of them's 3 volts. We're trying to figure out what this one is. And so we're going to add that there. So if I subtract those two, I have 9. And V2, we're still trying to figure out. Well, for that to equal 0, that means V2 equals 9 volts. So I have a 9 volt drop here. Okay, so let's solve for loop 2. See how it works over there. So I have my V0 minus V1, V3. We saw that in the previous slide. And here I have 12 volts would be there, just like it was up here. And I have my 3 volts, just like I did up there. Okay, so I just said that must be equal to 9 volts. And that kind of makes sense because these two are in parallel and there's no other resistance here. So that would have to be 9 volts as well, correct? Okay, let's look at a more difficult circuit. That was a fairly straightforward circuit. This one has a branch that comes up and over here, so we have some possible multiple current paths that can be happening here. So let's figure out our rises and our drops. So there is my rise, right? I'm going from a more negative to a more positive. There's my rise. That's the only rise I have in the whole circuit. The rest are going to be drops because they're resistive loads. So there's one drop, A to B, and I'm denoting that with a plus and a minus symbol. Here's another drop, B to ground. Okay, and there's my plus and minus symbol. And then here is another potential drop from C to B. So I'm going to put a plus and a minus there. Okay, I'm labeling this as V0. I'm labeling that as V1, just like in the previous slide, and that is V2. And then this will be V3 here. Here is my first loop. Okay, my first loop will be V1 and V2 back to my source. So remember, the definition of a loop is going a complete path from my positive, from one end of my source to the other end. I have to be careful because this could be an alternating current source. So I don't want to say positive and negative. From one end of my source to the other end of my source. Okay, I'm using a simple DC circuit here, but it could be AC. And my other loop is from one end of my source, or this end here, all the way back to the other end of my source down here. And that's loop 2. And that goes through V3 and V2. Okay? Okay, so loop 1. Let's look at this. Rise minus drop equals 0. That's our Kirchhoffs voltage law. We should be getting used to that now. And if we take V0 minus the sum of my drops, which is going to be V1 and V2, it should equal 0. And loop 2 is in this direction. If I take V0 and I take V3, because that's the first actual drop that it hits is V3, and add it to V2, because that's my only other drop in that loop. Okay, let's apply some voltages here and do some solving. So I'm going to say V0 is 9 volts, and I'm going to say V2 is 2 volts. Let's see if we can solve for the other voltages here. So I still have my formula here, rise minus drop equals 0. So 9 volts is my rise, and my drops are V1 and the 2 volts. Well, for that to be the case, 7 plus 2 would be 9. Subtracted from the 9 would be equal to 0. So that would have to be 7 volts. V1 right here would be 7 volts. Okay, so here 9 minus the V1 minus V2, that would also have to be 7 volts right here. So that is a simple application of Kirchhoffs voltage law. Now this can get quite complex, and I didn't want to get into very difficult circuits. I really just wanted you to understand the concept that the sum of the rises minus the sum of the drops need to equal 0, and that is Kirchhoffs voltage law. So I hope that helped. Check out another example that I have where we're going to go through an entire circuit using both Kirchhoffs voltage law, Kirchhoffs current law, and Ohm's law to solve for every component in that circuit. So that lesson will be coming up. We'll see you then.